Hello everyone. So in the last topic we covered cardiac output, stroke volume and heart rate. Well, now we are in continuation with the previous topic, and today's topic is venous return and fluid movement. But before going to the today's topic, we'll have a summarization of the previous topic. We have learned that cardiac output is the product of heart rate and stroke volume, and the factors that will affect the heart rate and stroke volume will ultimately affect the cardiac output. The heart rate was under the control of autonomic innervation by parasympathetic and sympathetic stimulations under hormonal action and exercises. There were also age-related changes as well as factors affecting the stroke volume like heart size, exercise, gender, contractility of the heart, duration of contraction, and diastolic volume like preload, total peripheral resistance like afterload were all the factors that were affecting the cardiac output. So now, what is venous return? Venous return is actually the return of blood to heart via veins, that are superior vena cava and inferior vena cava. Now these controls the end diastolic volume and thus stroke volume and cardiac output. So venous return is an indirect factor affecting the cardiac output via changes in end diastolic volume. So what are the factors that lead to changes in venous return? First is blood volume. So we know that if the blood volume increases or decreases, ultimately it will lead to the change in the venous return. Venous pressure. During the increase or decrease in the venous pressure, there will be corresponding sympathetic and parasympathetic stimulation that will lead to venoconstriction and ultimately causes increase in the venous pressure. So venous return will increase. Now there is another thing called skeletal muscle pump. So here you have to integrate your anatomy that you have learned in lower limb, that calf muscles are known as the skeletal muscle pumps of the body. Chiefly soleus is known as the peripheral heart because each contraction will lead to rise in column of blood which will be towards heart. Ultimately, this will also lead to increased venous pressure and therefore increased venous return. Now the third factor is negative intrathoracic pressure. So first of all, I would like to tell you to think in a way like wherever there is a pressure gradient for the fluids and gases to transfer in an energy independent process, there should be a pressure gradient. So when we inhale, there is a negative intrathoracic pressure, and due to which the air from outside can enter into a lung cavity. Therefore, in the same way, during inhalation, there is the creation of negative intrathoracic pressure and it is able to suck the column of blood towards the heart. So this leads to increase in the venous return as well during inhalation. All these factors ultimately will cause increase in the preload of the heart and therefore will increase in the stroke volume. Now let us move to venous capacitance. Veins hold most of the blood of the body, that is 70%, and are thus called capacitance vessels. Because they have thin walls, they can stretch easily and therefore they can accommodate more blood. Therefore, the thing which can stretch easily, which can have more amount of blood and can accommodate itself, that will have a higher compliance and they have only 10 mmHg pressure maximum. Now we have come to fluid dynamics, that is exchange of fluid between capillaries and tissues. So we know that there is a state of dynamic equilibrium of the fluid exchange between extracellular fluid or interstitium and in the capillaries. But there are two types of forces or pressures which are existing and are acquired by fluid. First of all of them is hydrostatic pressure. That is the itself says that pressure acquired by fluid. Here we referring to blood or plasma. So the property of hydrostatic pressure is to retain its property of motion. That is, hydrostatic pressure of the fluid will promote the fluid movement. So there are two types of arenas. So hydrostatic pressure exerted by the fluid present in the capillaries and hydrostatic pressure exerted by the fluid present in the interstitium. Both of them will try to drive fluid away from them. Now the next type of force is osmotic pressure or colloid oncotic pressure. This is the property of the fluid which is acquired by the proteins that are stored in the fluid. Now the property of this oncotic pressure is that they try to retain the fluid within themselves. Here also we have two arenas, that is the oncotic pressure within the capillaries and the oncotic pressure of the fluid in the interstitium. So ideally there is negligible amount of proteins or transudates or exudates in the interstitium. So the net oncotic interstitial pressure is 0 mmHg, whereas the plasma contains an oncotic pressure of 25 mmHg. Now on combining all the four types of starling forces or pressures, we can calculate the net filtration pressure. So we have four types of starling forces. So now we have said that all these types of starling forces or four types of pressures, that is hydrostatic pressure of the fluid in the capillary and in the interstitium, colloid oncotic pressure of the fluid in the interstitium and in the capillaries. On combining all the four types of forces, we can calculate the overall fluid movement on net filtration pressure. That can be best illustrated by the next coming picture. As we can see here, this is the hydrostatic pressure of the fluid within the capillary, that is trying to make the fluid movement outside the capillary, whereas the hydrostatic pressure of the fluid within the interstitium is trying to exert the fluid out of the interstitium. In the similar way, we have the plasma oncotic pressure of the fluid within the capillary that tries to retain the fluid within itself, and similarly happens with the oncotic pressure of the fluid which is there in the interstitium. And we have given all the four types of starling forces different kind of variables. So if you have to calculate the net filtration pressure, the easiest way is to do, you add all the components that are favoring the fluid movement, that is compelling them to move outside, and you subtract all the forces that are not in favor of the fluid movement. That will give you the net filtration pressure. So the filtration rate is product of net filtration pressure and the filtration coefficient. Filtration coefficient has a fixed value and it is represented by Kf. So we have learned that we can calculate the fluid dynamics by calculating the four types of starling forces. We have calculated and we have ultimately come to conclusion that there are other factors which are indirect, like venous return, blood volume, blood pressure, venous pressure, intrathoracic pressure, breathing, age related factors, gender related factors that are affecting the heart rate and stroke volume on a larger scale. They affected via preload or afterload, and therefore they also have the important role in affecting the cardiac output of a human body. Thank you. If you like the video, please like it, share it, and share your views. Or if you have any doubts, you can ask us in the comment section. Thank you.